Hey guys, hope you all are good. So we are back with our videos of interview preparation. Hope you have gone through the previous videos and hope you have liked them. If you have any feedback with respect to all those videos, you can let us know about them. Now we are going to discuss in this session about a pretty new problem, which is the trapping rainwater problem. Now you might have heard this problem beforehand at some point of time. You might have heard about this problem and you may have come across various solutions, and today we are going to actually combine all the concepts that we have used in some of our previous videos. We are going to see how all those concepts will yield us different solutions and how using all those solutions we will get better and better approaches and finally have a very good approach to solve the problem. So it will all start with a basic array kind of approach. We'll see how we are bettering from the basic brute force one to the best time complexity possible, and then we will gradually see how we can even better the statistics. So that being said, let us get started. And before we continue, please don't forget to subscribe the channel and let us know about what like how you're feeling about this. I'll definitely be notified about any particular feedback that you all may have. Okay, so great, let us proceed. Okay, so trapping rainwater problem basically is that you might be aware of the term rainwater harvesting. So what is done is some structure is built so that if there is this kind of a topography, then basically water gets stored over here. We know how according to Pascal's law water gets stored. So if there is some kind of elevation of this kind, okay, something like this, we can say that these heights, if we know all these heights, that what is the height at this particular point, what is the height for this point and this point, and we know all the heights, then from here we can infer that okay, this particular space, or we can say this total space shall be filled with water, right? This total space shall be filled with water. So imagine that you have bricks over here, these are all bricks, and above this water shall be stored. So in the leftmost point we have something like this. So basically no water can be stored here. We can understand that water cannot be stored here, water cannot be stored even here because that will flow out. We can see that water can only be stored here. This is a basic observation. So you can pause the video here, you can think about how we can approach this problem. I hope I'm audible and everything is fine. So the question is in this form that you have n non-negative integers, you have n integers a1 to an, a1 to an, and all the ai's are greater than equal to 0. And now from here what we can get is, we have to say that at a particular point or maybe in total how much water we can store. If a simple question is asked to you, just focus on this part. You can of course pause the video and think, but if you have thought about it, then probably you can again start thinking from this particular hint, that if I ask what is going to be, by the way, a1 to an, what sense does it make? Suppose n is equal to 5 and we have the array something like this, 4 3 2 2 5. Okay, then this basically means that it will look something like this. It will be 4, okay, it will be 4, and then it will be, next one will be 3, sorry, yeah, this is 3, then this is 2, and there are two such bars which are of or two bricks, you can say. This is how it will look like, and then you will have 5. So this is what it will look like. What can we say now? That over here basically this part is going to be filled with water. This set of two rectangles, you can say this part will be filled with water. So if you find out the area, this is going to be how much? 1 2 3 4 5 square units, right? So you have to mention how many square units basically are going to be filled. This is going to be the answer. So now let us proceed over here. If you have to find out that at this particular block, okay, in this particular block how much water can be stored, what can you say? I can store up to here. Why can I store water up to this particular height? Because to my left there is a brick which goes up to this height, and to my right also there is a brick which goes at least up to this height. It can be even more. So I know that if water is stored in this up to this height, that cannot flow away from any part. We know that it will stay still over here, like it cannot flow out from here, it cannot flow out from here. This is the idea. So from here what can we say? That if to my left, if I am at a place, to my left, right, there can be many different elevations, altitudes, and many other parameters. They can be totally shuffling, but at some distance, if I know that to my right all the pillars are having a height at least h, and to my left also, to my left as well as to my right, the pillars, there is at least one pillar to my left and at least one pillar to my right which has a height at least h, I can say that I have the ability to store water up to a height h. And using that approach, we can say that okay, let us find out what is the maximum that any of my bricks to my left does hold, and what is the maximum that any of my bricks to my right does hold. When I have the maximum, what do I know? That my left allows me to store a maximum, suppose max left kind of a height. Suppose I say that max left is the maximum height to my left. So what can I say? Max left is the maximum to my left, max right is the maximum to my right. So if I say I will take the minimum, max left and max right, I'll take the minimum. That minimum will tell me maximum how much height I can keep. So what is max left? Including me to my left, what is the maximum height of a pillar? That is, after which I will definitely be flowing away, the water will be flowing away, above which I cannot place. Max right tells that what is the maximum height that my right pillars will allow me. Any of the right pillars needs to have that kind of a height. So when I take the minimum, I know that okay, this is the height that both will allow me to retain, and hence I will say that okay, this is the basic thing. Now how much water can be added, that will depend on this particular height. When I want to suppose add over here, what can I say? That this height, this is the height from the sea level or from the ground level, whatever you say. So we know that this is that minimum height. So we cannot just say that this is the answer. We have to say that okay, this part is occupied by brick, so the rest of the height can be occupied by the water. What I'm saying is simply like this, that okay, if you are having up to here and this is the ground, this is the leftmost, like this is the topmost that your left guys allow, and this is the topmost, maybe something like this, which your right guys allow. You can say we will take the smaller one, and we will say this will be the distance that water can stay. So what will be this distance? You can say this height which we are getting by this minimum, we are getting this height minus this already present height. So we can say min of this minus h of I or h of current, whatever you say. Okay, so this is going to be the basic approach before we apply our head towards optimizations, time complexities. This is the basic approach, and you might recall we discussed largest rectangle in histogram. Now that was a very different problem, and we had many different approaches, but you can remember how we first of all changed our approach. We said that for the largest rectangle, if you have to include a particular index, if you have to include a particular index in the rectangle, and if you want to see that that index is totally, the bar in that index is totally included in the rectangle, then what we say is from there proceed to the left and the right and find out which is the last bar which is having a height at least this height. And we say that in case of both the left and the right, we say something like this, that if you have to make this the height of the rectangle, then go from this to the right, go from this to the left, and see up to where the heights are all greater than equal to this height. Okay, so there this particular approach came definitely as our second approach. This was not our first approach, but over here we can see that the first approach is only intuitive. What we can say is that at a particular x coordinate, you can say, or maybe del x means that particular 1 unit. I am saying that this is 1 unit, this is 1 unit, this is 1 unit, this is 1 unit. So for each of these 1 units, explore that how much your left guys and right guys will allow you to keep. And don't search for the nearest minimum, nearest maximum, nearest less, nearest less. Don't do that. Rather search for something like this, that what is the maximum that your left allows, what is the maximum that your right allows, and we can get for all I, this basically will give us the answer. For every I, this will basically be our answer. Make sense? Okay, so what is the basic approach? I hope this explanation justifies that why I have written this formula. Now if the question comes about the implementation, that okay, I've told a lot of stories, now let us look at the implementation. This is how the implementation will look like. You will have for I equals to 0, I less than n minus 1, I plus plus. You can say max left is equal to max of AR, or you can say H 0 to I, 0 up to I we are going to find out the maximum, and max right is going to be equal to max of H of I to n minus 1. So you can say that okay, if you have a sum like this, sum of the volumes of water which can be stored, so sum plus equals to min of max left comma max right minus H of I. Okay, that solves it. Let me check if everything, yeah, it looks fine. Okay, so what we are doing is basically that this minimum value minus Hi. Now what if that we don't have anything to our left which is greater than us? What if so? We know that since we are taking up to I is included in both, we know that max left and max right can be at most like the lower bound is definitely Hi. It cannot be less than Hi. So this min part will also be greater than equal to Hi. This min part will also be greater than equal to Hi. So when I subtract it, this will be greater than equal to 0 always. So if it happens that you are sitting at the tallest tower, then definitely like your surroundings can't help you to store any water. In that case, we'll get 0 over here. Make sense? Okay. Even if it is such that towards your left you have something very big, but towards your right everything is smaller of the same height, then you can't store, right? You can't store anything. You cannot store any water that will flow away from the right or whichever direction it is low, right? So that's it. This is the trivial approach. When you run this, you will find that you're getting the answer. But the thing is that max left and max right, what we are doing is these are basically order n approaches. What I wrote is that find out the maximum height in 0 to ith index and find out the maximum height in I to n minus 1th index. So this is order I and this is order n minus I. When you take the average, you will see, or basically if you take all the cases, you will see that this is order n, you will see that this is order n, and you will see that okay, this may have been a typo, so please do correct it. Basically, yeah. So so this is also order n. We are seeing all the blocks. Now yeah, you can actually keep it n minus 1. Why? Because from n minus 1 to n minus 1, this max right value will give what? H of n minus 1. So sum will be 0. So n minus 1 also if you keep, then it will not be a wrong answer. You can do from I equal to 1 to n minus 1. No problem. But whatever you do, all those finer optimizations won't be very productive. You will get order n square total time complexity. What is the space complexity? Can we say that it is order 1 space? See, we are not having any extra space. We are just storing this array. So when we say about extra space, we only talk about the extra arrays that we are making, the extra variables that we are making, and so on. So we can see that we are not making any arrays, we are not making any order in kind of spaces. So it's order 1 space. Makes sense? Yeah. Now, cool. But surely if n goes to 10 to the power 5, then this will not help us to get the correct answer, right? And hence this will not also satisfy the interviewer. If this is your last solution, then in most probability, more often than not, you won't be selected. So let us try to understand, let us try to drive our attention towards what can be the approaches to clear the interview. But before that, I hope this part is clear, and this forms our method 1, and whatever we do after this is going to be an advancement of the techniques we have used here or some optimization. So make sure you understand this well before you move on. Okay, cool. Next part is the method 2, and this is how it goes. What are we requiring? For every I, we are requiring the max left, the maximum left up to I, and the maximum to the right of I including I. These are the two things we are requiring for everyone. What if I say, since we are requiring the max left for all of them, can't we use some dynamic programming here? So this is a fairly intuitive thing. The thing is that, suppose this is your array, you have 3, 5, 1, 2, 6, 4. The max left, what is the max left up to here? Up to here we know the max left is 3. This is the maximum value. Up to here, what is the max? It is 5. Up to here, what is the max? It is again 5. How did we do it? We just checked whether 5 is greater or 1 is greater. If 5 is greater, then just keep 5. 1 is lesser, it won't help us at any different iteration. Then when you come over here, you again know that 5 is the greatest element till now. Then you meet 6, you say 6 is the greatest element. Then you say 6 is the greatest element till now. So what are we doing? We are doing simple dynamic programming. We are utilizing our previous values to form our next values. So using the simple optimization, what are we doing? We are simply telling that as you move forward, you keep on storing all the max left values. Okay, or we can say over here also, we can say that, okay, whatever was the max left, now update it using the HI. But the problem is that when you talk about max right, you have to find out for all those values. And this operation is not invertible. Like if I tell you the maximum of the last 9 items is this much, what is the maximum of the last 8 items? You cannot very easily tell me this is the maximum. Okay, if I tell you that the maximum the maximum of these items, I tell you that this is going to be suppose I tell you that the maximum of these items is going to be or let us think something like this: 5, 1, 2, 3, 4. I tell you that the maximum of these items is 5. Now I ask you, what is the maximum of these items? Next time I will move ahead, so right will now involve only I to n minus 1. So what shall we say? That over here, these elements, what is the maximum? Can I find? Just if I have 5 and if I have these values, I need to compute through each of them, right? I cannot suddenly, or else I need a tree set kind of a structure which will tell me something. But that will again decrease, that will again deteriorate the time complexity. So in order to find out the max right, it is important to store all the max right values. First of all, let us understand what approach we are discussing. I am telling you, store all the max right values and max left values. We have seen how to store the max left values. Let us see how we can store the max right values. From the right, we are checking what is the max up to a particular limit. Utilize the DP. When up to here, from here to here, what is the maximum? It is 4. So we'll write 4. Then from here to here, what is the maximum? It is the maximum of 4 and 6, so it is 6. Then the maximum of 6 and 2, it is 6, and so on, it remains 6. So we get all the maximum values in one go. Max right values we have obtained in one go. Max left values we can obtain from left to right, and max right values we can obtain from right to left. So you can see, I'll just write the pseudo code here. Suppose you have something like this: max left. This is an array or a vector of size n. Okay, int max right n. Now we will say that max left of 0 is going to be h of 0, is going to be h0, and for I equals to 1, I less than ni plus plus, if you look at all these places, max left I equals to max left I minus 1 plus h of I, right? Then for I equals to n. Okay, now we have to keep the base case for max right also. So the base case is max right I equals to, sorry, max right n minus 1, n minus 1 is equal to h n minus 1, and from here we know that for I equals to n minus 2 I greater than equal to 0, I greater than equal to 0, I minus minus, we can find out in the similar manner. This is the only thing that I mentioned. Max right I will be equal to max right I plus 1. Okay, I found out the summation. It won't be the summation, I'm sorry. So it will rather be the max. So you have to find the max of these two things. And over here also you need to find out the max of these two things. We can say the max of max right I plus 1 comma h of I, right? This is the only thing that we mentioned. And now what we can say, we can just copy this entire thing, this entire approach we can just copy. We can say, and by now we know that the terminal things, the leftmost and the rightmost, are not going to contribute, so let us not involve them. Let us, or we may include, there is no harm in that. I less than I plus plus sum plus equals to the min of max left of I comma max right of I minus hi. Okay, so by the end, by the completion of this algorithm, we will see that sum stores the value. So we can see that all these computations, pre-computations, take how much time? This pre-computation, let me change it. Yeah, this pre-computation takes order n time. This pre-computation takes order n time. This computation, all these are order 1 stuff. This finding minimum and subtracting, this order 1, and this addition as well. So n times if we do this, we'll basically get order n. Make sense? So the entire algorithm remains order n. Order n is the total time, and order n is the space. Order n is the extra space, you can see. Now from here you can actually understand what I was telling, that for max left you don't need to store it. As you move along from I equal to 0 to I equal to n minus 1, you can go on updating max left. You can still keep that as a single variable. But the thing is, max right, you need to store them. You need to store all these max right values because, okay, I think yeah, max right values, they are being formed from the right. They are being formed from the right. So that is the reason you need to store it. Another approach is you go on finding from the right cell, that what is the maximum that can be stored here, what is the maximum that can be stored here. You come from the right to the left. So over there basically the approach is going to be different, and as an advantage you can use the max right as a single, what can we say, you can keep that as a single variable. Instead of order n extra space, you can have order 1 extra space for max right, but max left will be requiring order n space for sure. Okay, so that's it. You can think of finer optimizations, but we can understand that it's not easy to get out of this too trivially. Now, why is the total time in the best form? Because we know that for all the different values, we at least need to read the values, right? So in order to find out the total sum, we at least need to read the values of AIs. So if you have to read n values, then the time complexity is automatically order n. So from there we know that, okay, total time has to be order n, and we are having the best time complexity as of now. So this algorithm that you can see in front of you, this is the best time complexity algorithm. But the side effect of this approach is that when we are moving from method 1 to method 2, we are making it space expensive. It is increasing from order 1 space to order n space, which is a bit of a worry for us. And for this, we'll gradually now move ourselves to the more advanced approaches. Now, these approaches that we'll be discussing now, the next two approaches, you will find that they are sort of omnipresent everywhere. You will find ubiquitously present. Everyone mentions all these approaches together, but what I'll do additionally in this video is try to develop the insights around why this works. I try to explain that particular thing, that why this approach is actually working. So over there I'll be spending the most of the time, and depending on the time and everything, I may like shift to coding it. That coding implementation won't be difficult, especially if you are aware of, if you have seen the previous videos, you could see that all those codes we could do in 15 to 20 lines. Even this one, whatever approach you choose, you will be able to code in a maximum of 20 lines or a maximum of 25 lines, depending on your own habit of implementation. It should not cross 25 lines, none of these. So I won't probably go into the implementations, but be very careful when I talk about the approaches. I'll be stressing on the insight. If you miss anything, please do come backward and listen to that. Okay. So let's proceed to the first interesting approach, first non-trivial interesting approach, which is usage of stacks. So the method 3 is using stacks. Okay, let us see how using stacks this can be solved. Okay, now we'll try to fill up in a different manner. Consider that they are single blocks only currently. Okay, I have made too many blocks. We'll be ignoring some of them. Okay, so maybe we'll do up to only here, or let us see. So yeah, I see that I have grown from here. This is basically my starting point. Before this I can't store anything. Let us focus from here. After this I see that I've decreased. Over here I know that I'm increasing. When I know that at a certain place, whether that is at the ground or above the ground doesn't matter, but if my predecessor is greater, and if the guy in front of me is greater, can I directly say that you can store water for sure? So it can directly say that yeah, I can store water over here. I can store water over here, at least up to here, because my left, immediately left person who is greater than me, immediately left brick, that and my right guy allows me to store up to this. I don't know anything else. And what can we say? We can say that yeah, between this left guy and this guy we can store this much water. There is no harm in it. Now what can we say? Between this guy and this guy we know this much water can be stored. We can also say that okay, now this guy, when we focus on this particular guy, for this guy, which is the next guy, this is the next guy which is taller than it, and to its left also there is some guy which is larger, and this is the first guy which is larger. See, here I am talking about the first guy which is larger, a very different approach, and try to map with the problems we discussed earlier. But let us see what we are actually trying to do. We are saying that for this particular level, you have something on the left which tells you that yeah, I am greater than you, and something on the right which tells you that I am greater than you, and both of them together say that this is a level which we can allow to keep. And I know that this is basically my previous guy who is taller than me, that basically starts at this particular x coordinate. My next guy starts at this x coordinate. So can I say that just cover this entire set of x coordinates, or this entire range of x coordinates, by this particular height which is the minimum of the two, minimum of this height and this height? That's exactly what we are doing. So we are storing up to here, and this is the height we have stored up to here. Now what can we say? Now this guy can now say that okay, I am done, like I don't have anything else to do, you can continue. So he will say that okay, to my left I've got something greater, to my right also I've got something greater, and the minimum of the two will tell that okay, I can store water up to here. Who can store? The entire range between this guy and this guy. So can we say that this entire range we are able to store water in it in different stages? First we chose the very bottom one, which has the least elevation. We stored water over there. We came one stage above, we stored water, and this is how we are doing. And let us see what actually we are using. Now we know that okay, this height is smaller. Now we'll move to this side, we'll move to the next side, we will see that okay, something is increasing. And for this, who is the predecessor? It will say this one. Can I say that since I am seeing something greater, I can immediately forget these guys? Because these guys cannot become the predecessor. Predecessor means the previous greater. Okay, so keep in mind the previous greater. So what can I say? For this guy, all these guys cannot become the previous greater, and for any other guy, these guys cannot become the previous greater. This guy will become the previous greater. So from here we directly know that we can ignore these guys. They have done their job. Now the predecessor of this guy is this one. What will it say? That okay, it is greater than me, this is greater than me, and the minimum of them will basically say how much water I can hold. And yes, the entire range from here to here, it can hold water. To what height? To this height. Can you check this? That up to this height I have stored the water. I have ensured that everything behind me has been stored up to here. Can you see? When we are moving the pointer up to here, when we have brought the pointer to this particular, oh, there are so many things, to this particular eye, what I've ensured is up to here everything has been filled with water. I've ensured because I am greater for those things, so I've made sure that okay, fill up everything that I am making you fill. And now as I'm moving on, I will say that focus only from my height. I find out the minimum from my previous greater, I find out the minimum from my next one, I find out the minimum among them, and then I'm storing this, okay, from this height. So I can get this again by minus hi. Again that same minus hi is going to give me the height. And what is the range? Now I have to multiply by the range, which is this particular range. It will be some del x, right? Del x times this h will give me how much water I'm storing at this particular stage. Can you see this entire part is filled up? Now let me walk you through the next stages. What we see is that okay, this is greater than this, so even this will tell us just forget yourself, get lost. It will say we don't require it, so this will also get lost. All of these will get lost, only this is surviving. It comes ahead, it comes over here. Now it says that okay, I'm smaller than you. Till now I cannot store water because in front of me there is nothing greater than me. Now it says, it comes here and says that okay, there is something greater than me, I can store water. Who is to my back? It is this guy. So we need to store it somewhere, that this is the previous greater. So we can say that okay, I can store it here and I get some water. Then when I go to here, I know that my previous greater, acha, before that I know that for this guy, when I've seen that I filled water for this, I can see for the previous one that yeah, this is also forming a low level compared to my next one and my previous one. So use their minimum height to even fill this particular height, fill this. Okay, so how we are doing? We are finding out the minimum, we know the hi, we are saying that this height needs to be filled, and that's it. That's basically it. So over here, if that elevation is taking place up to here or greater, whatever, then you can say that wherever your previous greater is there, till then you need to go and you need to fill it up. Okay, wherever your previous greater, so let us say the previous greater was exactly this height, you can say this entire part will be filled up. Clear? So you can see how stacks are helping us. Why stacks are helping us? Let us try to understand what will happen. What is the stack going to maintain? The stack will maintain something like this. Okay, let us say these are the heights. I'll write down the heights. So this is 6, this is 3, suppose this is 4, this is 2, this is 1, this is 5, this is say this is 1 as well, and this is 2. Okay, so now what I'm doing, I'm saying something like this, that first of all you're seeing 6 is greater, but for this guy there is nothing greater to the left, so you cannot store anything. If there is nothing greater to the left, you cannot store anything. You are finding 6. It doesn't mean that 6 has to be the greatest. Don't take me wrongly. Okay, before 6 you can have something smaller as well, which won't be able to store anything. Okay, so for this, when 6 is encountered, you will put 6 inside the stack. You will say that 6 is there for us. You can see the previous greater element we can find from it. Now when we are introducing 3, what do we know? That okay, 3 is less than 6, so 6 cannot store water due to 3 does not tell 6 that okay, I will allow you to store water. So what 3 will do instead, 3 will just enter over here, 3 will enter over here, 3 enters over here. Then 4 comes, or better, let me store the indices. It's going to be 0, 1, 2, 3, because for your implementation you require indices. Okay, 6, 7. So this is basically hi, and this is I. Now I'll mention indices. So first I introduce 0, then I introduce, or I'll just introduce hi. Okay, stack containing hi's, stack of hi, so that your understanding will be clearer. So you can see first 6 comes, 6 enters, then 3 comes, 3 says I'm smaller than you, I can't help you, so 3 enters. Then 4 comes, 4 comes and says that okay, I'm having something lesser than me, I don't require this. Whether it can store water or it cannot store water, that doesn't matter. If it can store water, I'll tell it store your water and just forget yourself. If it says that I cannot store water, I'll just say that get lost. So it says that okay, 3 can, this particular x coordinate can store water, so I'll say that okay, get popped and tell me what is your previous greater element. Its previous greater element is 6, or better we can say that the index is 0. From 0 to 2, or maybe after 0 and before 2, we can say this entire part shall be filled with water. Okay, so from this index 0 and from this index 2, we know that okay, this part is filled with water. And how much water? We find out the minimum of 6 and 4 is 4. 4 minus, what is the height of this? This is 3. So 4 minus 3 is going to be 1. So till now we have been able to store 1 square unit of water. Let us see. Next we check with 6, that is 6 greater than or less than 4 or equal to 4. If it is since it is greater, what can I say? I cannot overthrow it. 4 cannot overthrow 6. 4 will say that okay, be seated at your place. Maybe later I may find something greater than me, and then you can help me to store water at my place. Okay, so over here it actually says that 4 will not be removing 6. Why? Because when something greater than 4 comes, then that will be helped by this 6 to store water, something like this. So it will say that okay, remember this 6. It will just add itself over here. Then comes 2. 2 comes and says that see, I cannot help you to add water to yourself, and for myself I have to visit some other node, so for the time being I want to store myself in the stack. It stores itself in the stack. Then it says that okay, what I'm finding is 1. 1 also says I am smaller than you, so it stores itself in the stack. Then we see 5. Remember, I am storing the hi's. It says the 5, what does it say? That okay, I found something greater. So 1, if the height is 1, then please get removed. Tell me who is your previous one, who is greater than you. The previous one who is greater than you, it is 2. So it says okay. Then using the index which is 3, and we know that after this we have 5 after this particular index, so between that we can store water. How much water? We know that when we connect it, the minimum is going to play the driving force, so the minimum is going to be 2 and 5. The minimum of 2 and 5 is 2, and hi over here is 1, so 2 minus 1 is equal to 1, 1 plus 1. So when I remove this 1, I am actually adding 1 square unit of water over here. Next, what do I know for this particular index? I know that this is also lesser. Now when I cross this, how am I finding? See, the top of the index is this particular element. Okay, now it says that yeah, I am the smaller one. Now it will say that remove yourself because you are smaller than me. What is this me? It is 5. It is smaller than 5, so it will say remove yourself. So you have 4 before you and I am 5 over here. Between 4 and 5, yes, you are at a lower level, so we can help you to fill up. So there you go, we can have 5. Okay, I'm sorry. So while we'll be removing 2, we will say that okay, for 2, who is the previous element? This guy. And which is the next element which we are using? That 5. So between this, the entire part, please fill up with the minimum value minus hi. What is hi? This 2. Makes sense? So this part will be filled up. So we can say that the index is 5, or basically we can say 4 minus 2. This is the distance. 4 minus 2 multiplied by, this is the range, and now we will say the height. What is the height? The minimum of these two. The minimum of these two is 4 and 5. The minimum is 4. 4 minus 2, it will give 2. So the height is going to be 2. So we will know that 4 minus 2, it will give 2. 2 into 2, 4. So we have plus 4. So yeah, we can store 4 square units of water over here. So 4 plus 1 will give 5. And then we can say that okay, even now we are ousting this guy, which is 2. Now we are saying that even 4 is smaller. So 4 is smaller, then 4 will say that okay, I can also store water. Who is to my left? Who is to the previous greater? I will remove myself. The top of the stack says that there is 6. So from here I can utilize them and I can say that okay, the minimum of them will help me in keeping some water. And the minimum of them is going to be 6 and 5. So the minimum is 5. 5 minus 4, 1. So 1 into this particular distance. What is this distance? 4 minus 0. The positions will help here. So 4 into 1. 4 into 1. So this will again give 4. Right? Cool. So I hope the approach is clear. I think I can share a kind of pseudocode so that you can actually understand what is the operation I'm doing. In this way you can get a feeling that okay, we'll be able to cover. Now see, when I'll be crossing this, what shall I say? I cannot oust 6. So 5 I'll be adding over here, right? And then see, now 6 will not help me anymore. I can see that 5 is the greatest. Now after this I won't meet anything greater than 5. So if I don't meet anything greater than 5, then I cannot move to 6. I cannot utilize 6. So yeah, everything won't be utilized. But yeah, so let us see. We can initialize a stack initially. Stack. Yeah. So this is a kind of pseudocode, you can say. So for I equals to 0, I less than n, I plus plus. Now what can we say? That while and stack, this will basically, this is st and this will store the positions. Okay, so we were storing the hi's, it will store the positions of hi. Okay, so they will all be unique, and from there I can also understand that okay, how to fetch the positions and subtract to get the distance. So what is my formula? First of all, my basic formula is going to be something like this. It will be the summation of these things, the distance that we get multiplied by, distance is not a constant, it will change, multiplied by again that thing, min of prev max and next max minus hi. Okay, so when we do this over all I, we'll get the answer. So the distance is what, like you can see over here as well, the way I'll be coding it. While st dot empty, it depends on the programming language that you are using, or you can say st dot size is greater than 0. st dot empty, I think it will be better, that while it is not empty and st dot top or peak, it depends on the language. st dot top, we can say that h of st dot top is mm, less than, it is less than h of I, whichever is a current element. Okay, then basically we'll be removing that element. We will say, yeah, pop it first of all. So int j is equals to st dot pop, or you can see what your languages support. You can do peek and then pop, you can see according to your languages. Then we can find out, we have got j, what else, yeah, so if now you have popped out, so it is gone. Now we will check if it is empty. If st is empty, then you can just break it. If this is empty, then please do break it. Why? You don't have anything greater than it before, so there is no use lingering over here. And yes, if it is not empty, then you can see, then basically your summation, you will have sum equal to 0. So sum plus equals to whatever will be your previous element. We can do something like this. The distance is going to be I minus 1 minus st dot peak, the previous index. So this is the distance multiplied by the minimum of the next one, which is hi, comma, right, hi, and the other one is h of st dot peak. Okay, there you go. So yeah, we are not removing anything over here, we are just doing peak. Now when you do this, after this the required operation is to push. So you'll be pushing this st dot push only I. Okay, and this should be sufficient. When you have something remaining left in the stack, then at the end you don't have to worry about it, they won't be able to store anything. What is one property of this stack? This should be clear. One property of this stack is there is a monotonic data structure. It is storing values monotonically. You can see always, you can see we are currently storing only 6 and then probably 5 and then 1. 2 will come and it will push away 1. So it will store 6, 5 and 2. So it is always storing elements in decreasing order. If anything comes which is greater, it is removing the elements which are smaller. So it is always storing in the decreasing order. So this is a kind of monotonic data structure, or you might have heard the concept of monotonic queue. So yeah, this is also that kind of, it is actually the example of a monotonic stack. Makes sense? Cool. So by this, if I would have written it in an editor, probably I would have been able to run it, but that is not important. You can try coding it yourself. You'll find the code everywhere. That is why I didn't stress on executing and showing you. You'll find these ideas and the implementations everywhere. They'll be pretty much the same, so you can try it yourself. But I hope this idea is clear, and see how we are again approaching it, how we are using the next greater and previous greater. Next greater and previous greater doesn't mean that they will determine the height, but up to an extent it will determine the height, and we can see how it is finding out the answer. Okay, this thing is important. This range is important. This range is taking care of that. I am only not worrying about my own thing or my previous thing, the one that I'm popping. I'm not worrying about only the one that I'm popping, but I'm worrying about everything that lies in this particular range. What is the range? I minus 1 and st dot peak. I'm worrying about everything in that range, from st dot peak plus 1 to I minus 1. Okay, that is why I did this minus 1. You can check this, like whether it is matching or not. Okay, but what is the time complexity now? Time complexity is order n. And what is the space complexity? Space complexity varies, but it can definitely go up to order n, and it will not go up to 2n. One thing that we were facing in the previous approach, it won't go up to 2n. And if you can say this approach to your interviewer, there are fairer chances than the previous approach to crack it. Okay, so although the statistics is the same, we have order n time, we have order n space, and the space is not 2n, it is exactly n, or at most n you can say, and it is a good approach. It is not that trivial an approach, it is a good approach. Okay, but we have not really improved the statistics. So now the challenge arises for us to improve the statistics. So let us move ahead and let us see if we can do the same as well. Method 3 we have done, so method 4 we'll be doing over here. Method 4, okay, we'll be using 2 pointers. Okay, suppose that this is from index 1 to n, and please pay attention, this is the moment when I expect you to pay attention, okay, because this approach requires very good absorption of the insights. I'll share the insight and I'll try my best. What you should do from your part is try your best as well, then only we can get this successful, right? Okay, suppose I am at these two indices and I know that, okay, for this guy, like I am over here, this is I and this is j. In some manner, if I come to know that this is the greatest element among the first I elements and from the last j elements, okay, observe what I am telling. In this range, union this range, this is my maximum element, okay, so this is the max in 0 to I, sorry, 1 to I, or we can say, okay, 1 to I union j to n. This is having like the max hi. Hi is the max. Hi is the max pillar. Before this everything is smaller, and after this also everything is smaller. It can be greater than this, but it is definitely smaller than this, okay. From here what can we say? The important thing, can we infer from here that if we reach such a stage when we know that hi is the maximum of those two ranges, what do I know? For this j, what do I know? That basically the maximum height up to here, the maximum height to the right up to here, this maximum height and this maximum height, if I do the minimum is going to give me the target height, right? If I find out the maximum height up to here and the maximum height up to here, then the minimum of that is going to give me how much can be my height for storing the values or for storing water. And what else can we target? Yeah, those two things if we do, then minus hi will give me the water. But up to now I don't know anything about this particular range. I don't know anything. There may be something very high, there may be something very high, I don't know. But can I say something that it doesn't matter if I have anything which is very less or very high, or it doesn't matter? Can we say something like this? It turns out that yes. Why so? See, this guy is the greatest you have seen till now. This is the greatest. Everything else is smaller. When you find the minimum, where will this minimum lie? If you find out the minimum of this guy and whatever you will have from its right, the maximum from its right, suppose you have got the maximum from its right. If you know the maximum from its right, and you know that if you are proceeding in this manner, okay, forget about how you will find the maximum to its right, but suppose you know that you know the maximum from the right, you don't know the maximum from the left, but you know the maximum value, you know that the maximum from the left is this guy, and this is greater than me, and this is also greater than everything I have over here. This is greater than all of these elements, or at least greater than equal. What can I say? That I cannot definitely cross this height. The water level will definitely be bounded by the minimum of my right pillars and my left pillars. My left pillar, I know that this is present. So after this, if anything is present greater than this, if suppose some other pillar over here is present to this particular height, can I say I can raise the water level? No, right? Because my right people, they have said that we are all less than equal to hi. They are all less than equal to hi. So if we have something even greater than hi, it doesn't matter. And suppose you have something smaller than hi, then I think it is, by now it is understood, if you have something smaller than hi, it doesn't matter, because this is going to drive, this is going to basically dictate how much water is being stored. Now we are focusing on how much water we will be storing over here. Okay, how much water we will be storing over here. We are focusing only on this part. That's it. Don't worry about the range and those things. We are worrying about how much you can store in this part. So what can I see? If I know that the maximum from the left is at may not be at I, but the maximum from the left and the maximum from the right, maximum from the left up to I and the maximum from the right up to j, the maximum of these two things is at ai. If I can show it, I don't know if it is possible, but if I can show it, I can say that I am done. Now if you have the max right, then yeah, max right is going to tell me what my minimum value is going to be. If this is the maximum, then max right is going to give me the minimum value. This is the minimum value. So I can say max right minus this 8j is going to give me the height. I can just store that height. Make sense? Okay. So now the thing is, how can we find it? We'll basically try to find out this particular thing that I explained. For any I, now think the opposite case. If I know that this is I, this is j, by now what are the things I know? Hj is equal to the maximum of h of 0 to I and the heights of j to n. Okay, n minus 1 you can say, 0 indexed. Okay, so this is the maximum in this range and union of this range. Okay, the maximum of this and maximum of this and the maximum of both of them is going to be hj. Suppose it is the case, what can I say? That till I, suppose we have got some value which is nothing but max left of I. Okay, we have the max left of I. So what can we find out from this? We have hj, we have the max left of I. Max left of I is definitely going to dictate how much can be present, because this is always going to be greater or greater than equal. I know that hj is greater than equal, so I can simply say that the height that can be stored is max left of I minus hi. This is the amount of water that can be stored above it. Okay, this is the amount of water that can be stored above it. So we know that if we have this kind of a two-pointer arrangement, then the rest of the thing is easy. Suppose from here I give you the task that up to here I have got this arrangement, that suppose this case we are taking, that the greatest element is at I. Can we say now that I will not store any water, I won't be storing any water, j has already stored water, j won't be storing any more water, we know that j won't be storing any more water, and if I move away from here, then the problem is that I will stay at these two positions, I plus 1 and j. So there are two things in two-pointer approach. Think that I and j are at a certain place, and at a certain point you can either move I forward or j backward. If you move I forward from this particular stage, the thing is that I plus 1 and j, maybe none of them are the greatest element, right? Maybe none of them are the new greatest element. Till now what did we have? From the left and from the right, we had the greatest element at hi, at I. Okay, that was hi. Now if we move I from there, maybe I plus 1 and j, none of them can have the greatest element, it remained at I, right? But if we move it here from j to j minus 1, can you see that there are two possibilities? If you find some very big element, then you can say that till now whatever elements we have seen, this is the greatest element. And if you see that this element is smaller than hi, you can say that hi is the greatest element I have seen till now. Can you see? If it is greater than hi, then j minus I is the greatest element seen till now. And if it is less than hi, then hi remains the greatest element. If it is less than or equal to hi, then also hi remains the greatest element. So the thing is, over here you can see that we are either ending up in this case where our new ij again has at least one of them as the greatest element seen till now, from the left or from the right. Okay, and we can say that over here also, in this second case also, we have the same. Okay, so that's it. These are the two cases what we are considering. We are having ij, these are the two pointers. Case 1 is if hi greater than equal to hj, or you can say greater, hi is equal to greatest element, okay, in 0 to I. And case 2 is that hi is less than hj, and in that case hj is the greatest element in union j to n minus 1, and here also 0 to I union j to n minus 1. Now the thing is that from here you can easily find out, you can easily make it hold. When you know this kind of a thing holds, it is very easy for you to find out. From here we can easily find out how much water j will store. We can easily find out that. From here we can easily find out how much water I is going to store, right? And we can gradually cover all the vertices by moving in this manner. Whoever is the greatest, that will remain over there. So what is the approach we are using? This should be now quite clear. We are using this approach, start from the extremities. At the extremities, you know that 0 to 0 and n minus 1 to n minus 1, you basically have this kind of property that out of these two elements, one of them has to be the greater. So yeah, it holds. When you move to the next step, whichever is smaller, move that to the next step. The greater remains at its position. If you get something even greater, well and good, you have got the greatest element, else that is the greatest element. Okay, so let us see for the making an elevation map how it works. We have something like this. Okay, this is, the indices are 0 1 2 3 4 5 6 7, and the heights are 2 4 5 3 1 4 5 3, right? Yeah, so these are the heights. Now what can we say from here? First we are at these two things, I and j. What can we say? Which is the greater? This is the greater. Using this greater, I know that the max left. Now what is the max left? ml and mr, these are the things I'm keeping. Max left is 2 and max right is going to be 3. So what do I know? That the minimum is basically the max right is not important, I can just say the other one, but anyway, whatever it is, I know that if this is smaller, then the other one is actually the max right, it has to be. Okay, now we'll be proving, or we'll be basically convincing ourselves through this example. I know that there will be no water over here. Now this is smaller, so what shall I say? That move one step. I think this is going to take quite many steps. Let us choose a better example for an easy kind of analysis. So we'll have something like this, then we'll have something like this, then we'll have something like this, we'll have something like this, and then we will have something like this. Okay, now see, I'll not place all those values now. I'll just show you how this works. I and j. Now see, where at I j tells that I can't store anything now. Forget me. I'm okay. First of all, let's focus on only how we are always maintaining the largest element in either hi or hj. Largest element seen till now from the left or from the right. What we are saying that till now in these positions this is the largest element, and yes, we have it. We have I over here, so yes, this is the largest element. We have it at I. Now this smaller element will be basically moving the j from here to here. Now what do we know? That among this element and this element, which is greater? This element is greater. We know that this element is greater. So we will say that now shift I, whichever is a smaller element. Now see, among these two elements, can I say that this is greater and this is the greatest element you have seen till now? Even in the previous step, when I had I over here and j over here, can you say that this is the greatest element we have seen till now? Now let us move j. This is smaller, let us move j. It has become even smaller, but can you see that the greatest element seen till now in this range and in this range, this is still at I? Why? Because we are keeping the greater element fixed and we are moving the smaller element only. Okay? Like you might have also actually seen people who participate with 3-4 CodeChef IDs, or might have participated at some time. So you might have seen that when they do so, they usually, what they do is, whichever ID has the least CodeChef or CodeForces rating, they work on that, so that if that increases, well and good. If that does not increase, at least the maximum is retained. Okay, so this is the approach. When you have multiple IDs, now I'm not encouraging the same, but you can see this kind of strategy is actually employed by many. Okay, so we are doing the same thing. We can say that the maximum is in our control. Whatever is lesser, we are moving that. Among two, we are always getting the choice. We are saying that okay, let's move it, and yes, by moving it, we are getting the greatest element now. Next time we'll move this. We'll move this because this was the greater element. Now also this is the greatest element we have seen till now in this range and in this range. Okay, this is the greatest element. And then we can say we'll move this and we'll move this and then we'll move this, and you can see that all the places are covered with either I or j. Can you see this? In any sequence, the sequence can be anything, but all the i's and j's are covered. You can say that at the end some j is left. You can say whichever has the highest height, whichever has the largest height, we are not concerned about it. Whichever has the largest height, no water will be stored on top of that, so just forget it. Now can we do even better? Over here, can we break into three cases? Yes. If we break into three cases, you can see if hi is equal to hj, you can actually move both the pointers frontward. You can actually do this. Why so? Because we know that both are greatest elements. If both are greatest elements, just a second. No, just retain one convention. That will become a bit of a problem. Yeah, that will become a bit of a problem unnecessarily. But over here, what you can see is that if my hj is smaller, so over here I have actually told you by induction at any point of time we can actually ensure this thing, that either hi or hj is the largest element in h of 0 to I union h of j to n minus 1. This one I have proved using this particular example, you can say, or I have also shared the ideas of proof. Okay, right? It's basically when you reach at any vertex, whenever you have reached a vertex, you will not leave it unless you find something as good as this, okay, or greater than this. That means you are holding tight that greatest element. So the greatest element must be one of hi and hj. Once we know this, the rest is easy, because I've shown you that if we know that one of them is the greatest element, I can find out the amount of water in the other one. But the important thing is we need the max left and max right. But over here, because I'm having only 2 pointers, I don't need to store all the values. I just need what is the max left up to I and what is the max right up to j, and only these values, these two values, not up to j plus 1, up to j plus 2, and not all those things, not up to I minus 1, I minus 2, and all those things. I want only up to I from the left and up to j from the right. Make sense? So we can look at the coding implementation in short. Maybe it should be easy. Max left, you can say max left is, okay, I'll do this from scratch. So I equals to 0, j equals to n minus 1, max left is equal to h of I, max right, I'm sorry, h of 0, and max right is equal to h of n minus 1. Okay, yeah, h of I was also fine. So okay, while I is less than j, why am I doing I less than equal to j? Because the last one doesn't matter, that is the largest, so I'm keeping it. You can place I less than equal to j also. If while this is so, if hi is greater than equal to, or we can say less than equal to hj, that means we'll be changing I. In this case we'll be changing I, but before we are changing, we again have sum equal to 0, suppose. So sum plus equals to, see, we are again going back to our initial approach where every x coordinate wise we are actually processing it. Sum plus equals to just a second, yeah, min of, we can say that hj is the greatest element. Okay, if hj is the greatest element, min of hj and max left is going to suffice. But I think you can do this. Max left equals no, when we'll update it, we'll be doing that. Max left, yeah, minus h of I, this should suffice, and then I plus plus. When we have done I plus plus, max left now is going to be, why have I done I plus plus? Because hi is less than equal to hj. Hj will contain the maximum, whether it is equal or the other one is lesser. Max left is going to be equal to the max of max left comma hi. Makes sense? Else what shall we do? Something like this. Else sum plus equals to minimum of hi comma max right minus hj. Makes sense? And we'll say j minus minus, because j is the smaller one. We have filled water and we are done. We don't need to see anything between the I and j to find out if we can store more water. That is not possible. Max right is equal to max right, I'm sorry, max of max right comma h of j. Okay, that's it. There you go, while I less than j. Yeah, so this is a complete algorithm. You can see that there are only two variables, and now there is no order in space storage, no order in storage at all. Only h is there, that is the input array. But you can see that no extra space goes to order n or something related to input size. So now our approach is, you can see that at every iteration of this while loop, either I is increasing or j is decreasing, and initial difference between I and j is n minus 1, and so there will be at most n minus 1 steps. Okay, so we can say this is order n time, because every iteration of this while loop actually takes order 1 time, this simple order 1. So order n time, and how much space? Order 1 space. Make sense? There you go. So I hope the intuition was clear. I hope you all are convinced that the implementation was not that difficult and connecting the dots has not been that counterintuitive or you know against our cognitions. So anyway, you can revise this yourself and you can try implementing it yourself. You can check the implementation because I have not tried it in editor, so there may have been small typos. You can check that yourself. Before I finish, let us summarize what we have done. So this is one of the most critical questions which have been asked across product-based companies interviews, across FANG interviews. And it will be nice if you are aware of all the approaches. Method 1 was our brute force. Method 1 was our brute force, and we have done it using order n time and order n space. Method 2 was using arrays. We have done it using order n time and order n squared time and order 1 space. So yeah, this was order 1 space. Over here we used order n time, order n space. Method 3, using stacks, we did order n time, order n space, but the differences here, according to the naive implementation, we saw that 2n spaces are required, here n spaces are required. Unless we optimize one of the max left or max right, here 2n spaces was required, here n spaces are required, or you can say less than equal to n. It is not always reaching n, okay? But we can easily form an example, but if you look at the average thing, it will not be always n. Method 4 is using 2 pointers, which is the best approach, and by now I hope you are convinced why it is the best approach. We are taking order n time and order 1 space. Make sense? So if you have understood these 4 approaches, and if you are also comfortable with the intuition that we used behind creating these approaches, then you are in a good position to attempt related questions in all your upcoming interviews. So all the best for it. And before we finish, actually this could have been towards the beginning. Anyway, like, okay, let's leave it. I don't think I need to spend some time introducing myself. Okay, you can subscribe the videos. You can let us know what you feel about the video. Okay, great. Take care and all the best for your interviews.